My name is Thomas Kvarnström, and I will be guiding you through this Microservices Architecture Overview module. Let's get started. Why are so many organizations interested in microservices? Microservices can help making releases more stable and faster, and also help organizations encouraging change. In a monolithic architecture, the culture is often to not encourage change, and mantras like "don't fix what isn't broken" are often used. Breaking up a large monolith into smaller services that are developed and maintained by small efficient teams will foster a culture where change and continuous improvement is embraced. One explanation for the "don't fix what isn't broken" culture is that the organization is already fighting with big complex releases that are risky, and therefore additional changes are discouraged, even if that change is an optimization to make the application run faster. DevOps and continuous delivery has taught us that smaller incremental releases, preferably one change per release, is what we need to make the organization embrace change. The problem is that a monolithic architecture may consist of hundreds and thousands of lines of code that are fragile and take a long time to build and test. By breaking up that monolith into smaller services that are released independently will help organizations to adopt DevOps and continuous delivery. If changes can be pushed to production in minutes instead of weeks or months, it means that the organization can more quickly adapt to market opportunities, regulatory changes, etc. More frequent releases also leads to higher efficiency in the teams. For some organizations with high performance requirements, microservices also enables them to scale individual services, which saves resources and eliminates bottlenecks instead of scaling the full monolith. Let's move on and discuss what constitutes a microservices architecture. The definition of microservices will vary somewhat depending on who you ask. So instead of looking at the definition, we will describe a set of core principles that most experts agree on. First thing is module around your business domain. To define the boundaries for the microservices in your architecture, domain-driven design are recommended. Another core principle is to adopt a culture of automation. As the microservices architecture grows, so does the importance of automation. As we touched upon on the last slide, without automation, parts of the value proposition for using microservices will be lost. It's also important to allow these services to deploy, scale, and release independently. Each service should have its own life cycle and should not be dependent on other services to release a new version. We also have to consider that even though they are loosely coupled, microservices does depend on each other to provide a complete system or application. Because of that, microservices have to be designed to be anti-fragile, so that if one service is lost or responding slowly, it shouldn't affect the whole system. An organization that embraces microservices should empower each team that are developing a microservices to choose the programming language and frameworks that is best for solving their business domain challenges. At the same time, an organization will benefit from having common features like aggregated logging, orchestration of runtime services, failover monitoring, etc. It's a balancing act, but it's important to understand that microservices spans beyond one single programming language or framework. To embrace change, microservices should be API focused, and it's each team's responsibility to make sure that the API are backwards compatible, etc. Another thing that is important to allow for independent releases, etc., are decentralized data management. Each service should be responsible for its own data store and not dependent on a central data store. These core principles are not written in stone, but deviating from these principles should be a conscious decision. Using containers when building microservices allows freedom for each team to choose the tool they believe are best suited for implementing a service. By packaging the service as containers, the services can in an easy, consistent way be deployed into both test and production environment without any change. In a block diagram, most microservices will look very similar, but the content of the block may differ a lot between services. For some services, a Node.js application using JavaScript might be the best option, while for others, Spring Boot or a lightweight Java EE application server like JBoss EAP are the best option. As the number of containers grow, it quickly becomes impractical to manage the containers individually. OpenShift Container Platform makes it easy to manage a large set of containers that can automatically scale up and down as needed, and can offer high availability for containers regardless of what programming language is used. OpenShift provides a lot of features that matches the core principles of microservices, like, for example, deploy and release and scale independently, CI/CD tooling like Jenkins, but also source-to-image build assistance so that developers doesn't have to care about container formats or best practices. It makes services anti-fragile by providing infrastructure for health and liveness checks that can restart a service that is not working properly. It's also polyglot since it supports many different programming languages and frameworks, and a lot more features that are beyond the scope of this demo. Using OpenShift Container Platform, one can select between many different programming languages, frameworks, and data stores. In a microservices architecture, different services have different characteristics, and for some, a NoSQL data store like MongoDB is the best fit, while for others, a relational database like PostgreSQL are the best. Some services might also find benefit from being developed in another language, like using Node.js for mobile application development, while other services are best implemented in Java. This slide shows just a few of the products and community projects that OpenShift supports. Before we jump into the demo and see how OpenShift can support a polyglot microservices system based on many different services, let's spend some time talking about the architecture of the demo application. At the top is the web user interface, which is implementing using Node.js and is using a popular web framework called AngularJS. AngularJS, in its turn, are talking directly through a gateway service, which will route the incoming traffic and act as a gateway, so we can aggregate data from multiple services to provide more intelligent endpoints. The gateway service is implemented using Fuse Integration Service and are built as a Spring Boot application using Apache Camel. Below that, we have the inventory service that provides live information on how many products we have in stock, and that one is implemented using JBoss Enterprise Application Platform and PostgreSQL. We also have the catalog service that is providing detailed information about each product and is built with JBoss Web Server or Tomcat using a MongoDB data store. The cart service is used for the shopping cart functionality and is also built using Java EE and JBoss EAP. With that, let's move directly into looking at how the demo looks like. So this is the demo interface. As you can see, it looks like a normal retail store with different products that you can shop. So you can add things to the shopping cart. You can see that there is an inventory status. You can select multiple things as well. And this is the status of your shopping cart. And from your shopping cart, you can remove things to update it. And everything you see here are different microservices. So let's dig a bit into the different microservices. So as you can see, the interface allows us to minimize and group things together. And the web UI is built in Node.js, and it's you can see it's using very little memory and basically no CPU right now because the load on the system is basically 0. But it's a very efficient way to do a web UI. We also have the inventory service. So the inventory service, it's using a bit more memory and it's built using JBoss EAP. And if we drill down into JBoss EAP, into here, you can see we can look at some more detail about the metrics. So obviously a Java framework will use a bit more memory initially, but it doesn't necessarily use a lot of CPU. And the reason it's using more memory is because it has its own memory allocation. So you can see this is based on an image called EEP7, and we can actually log into the terminal, to the actual container. We can see that this is the only processes running in the container. So using containers, it's very clean and only reports a few systems in there. If we move on to the database, you can see that it's an inventory. It's data using PostgreSQL. And that one, in its turn, is actually using a persistent storage to make sure that we don't lose data. It's a read-write once storage. If we move into the catalog service, the catalog service is using a MongoDB as a background and is implemented using JBoss web server or the community project called Tomcat. So if we log in here, we can see JBoss web server, Tomcat based on Tomcat 8. It's using a bit less memory. Memory will, however, fluctuate depending on load. And then finally we will check out the gateway as well. And if you remember, I mentioned that the gateway was built on Spring Boot. So in the log file we should see Spring, as we can see here. But actually what's running here is a camel work. It's a camel process, camel work pipeline that is gonna do the aggregation between different services. And also some failover. Thank you. That concludes the Microservices architecture overview module, but please check out the other modules for more detailed information about things like resilience, etc. Goodbye. Thank you.